Welcome. Today we will be studying chemistry, and in that we will be studying chapter number 9, coordination compounds. Now coordination compounds are studied in coordination chemistry, and coordination chemistry is the most amazing field of inorganic chemistry. It basically deals with the transition metal complexes. Not only transition metal but some non-transition metal also form complexes, and these complexes have many biological, industrial and analytical uses, and hence their study becomes important. So let's start with the introduction. We will first start what is coordination compound. Coordination compound consists of a central metal atom or ion surrounded by atoms or ions. So let's begin with example over here. This is a cisplatin compound. It is a coordination compound. It is a platinum complex. Cisplatin is used in cancer treatment and it is a chemotherapy drug. Now look at the structure of the cisplatin compound over here. You can see platinum is situated at the center. So platinum is central metal ion over here, and you can see it is surrounded by 4 molecules, out of which 2 are of ammonia and 2 are of fluoride. So what are these surrounding molecules or atoms called as? They are called as ligands. Now you must be wondering how these ligands are attached to the central metal atom. Now these ligands are attached to the central metal atom through a special type of bond known as coordinate bond. Coordinate bond is a type of covalent bond in which the shared pair of electrons are donated by one of the species. That species over here is ligands. Normal covalent bond, we know that it is formed when 2 species involved in the bond donate electron pair equally. But in coordinate bond, the bond is formed when one of the species wholly donate the electron pair. So now here we will see with the help of example with the here. Here now platinum is forming 4 coordinate bonds. It is forming with ammonia, this chloride and this chloride. So total 4 coordinate bonds this platinum ion is forming. Now the coordinate bond is represented by an arrow, and this arrow is started from the donor atom and it is pointed towards the acceptor atom. Now we have seen that there are 4 coordinates bond in this molecule. So let's draw the coordinate bond pointing towards the metals. So we can draw like this, from this chloride, from this nitrogen and from this nitrogen of ammonia. So this platinum atom or ion has 4 coordinates bond formed with 2 ammonia molecules and 2 chloride ions. Now why is this central metal atom accepting electrons? Because it is electron deficient, and the surrounding atoms or ions, they are called as ligands. Why? They are donating electrons, so they are electron rich. In other way we can say that central metal atom is acting as Lewis acid. You know the definition of Lewis acid and Lewis base. Lewis acid is any species which can accept electron pairs, and Lewis base is any species which can donate electron pairs. So this coordination compound can be considered as a Lewis acid base interaction in which your central metal atom or ion is Lewis acid and the surrounding molecules or ions are your Lewis bases. Let's move on to the next topic, that is the type of ligands. Now ligands are classified based on the type of number of donor atoms they have. So there are 3 types of ligands. First one is the monodentate ligand. Now as the name suggests, mono means single. So this ligand has a single donor atom which can donate a lone pair to form a coordinate bond with the central metal atom. Now here are the examples of monodentate ligand. This is the chloride, this is hydroxide, and this is cyanide. So in this chloride, chlorine is donating a lone pair of electrons to form the coordinate bond. In hydroxide, oxygen will be donating its lone pair of electron, and in the cyanide ion, nitrogen will be donating its pair of electron to form coordinate bond with the central metal atom. Let's move on further to the next type of ligand, that is polydentate ligands. Now poly means many. So polydentate ligands are those ligands in which there are two or more donor atoms which can form coordinate bond with the metal. Now if the ligand is having two donor atoms, then the ligand is called as bidentate ligand. If the ligand is having three donor atoms, the ligand is called as tridentate ligand. If it is having four donor atoms, it is called tetradentate, and hence on. Okay, so here we will see an example of a bidentate ligand. Now look at the structure over here. The example of the bidentate ligand I have taken here is ethylene diamine. This is the structure of ethylene diamine. You can see that it consists of two nitrogen atoms. So each nitrogen carries a lone pair, and each of them can donate a lone pair of electron to the central metal atom. So one ligand of ethylene diamine can form two bonds with a central metal atom. So it is known as bidentate ligand. One more example of bidentate ligand is there, that is oxalate ion. Oxalate ion is also a bidentate ligand. Now the next example is of EDTA ion. EDTA is a short form of ethylene diamine tetraacetate ion. Okay, so let's see the structure of it. This is having acetate group over here, one more acetate group attached to the nitrogen. This nitrogen also has acetate. So now you can see this EDTA ligand is called as hexadentate ligand. That is, it can donate 6 pair of electrons to a central metal atom. Now let's have a look, how does it donate 6 pair of electrons. Now we can see here 2 nitrogens are there. So each nitrogen will donate 1 lone pair of electron. 4 oxygen atoms are there. Each oxygen atom will donate 1 lone pair. So total 6 atoms are there, each donating a lone pair of electron to the central metal atom. Hence total 6 atoms are there which can donate lone pair of electrons to the central metal atom, and hence EDTA is called as hexadentate ligand. Now these polydentate ligands, they form rings with metals, with metal at the center. Hence they are also called as metal chelate. And the ligands, since the ligands are forming rings, so they are also called as chelating ligands. I will show you with the help of an example. ethylene diamine. Now this nitrogen and this nitrogen. Okay, this will form ring with a metal at the center. Okay, so that's why they are polydentate ligands are also called as chelate ligands. The third type of ligand is ambidentate ligands. Now what is this ambidentate ligands? Ambidentate. What do you understand from the name ambidentate? Ambidentate ligands are those ligands which have two atoms which can donate electrons, but they uses single donor atom at a time. Single donor atom at a time. Let's understand it with the help of example. Now this nitro atom over here, the nitrogen can donate electron to the metal, or oxygen can also donate electron to the metal. So at a time only sometimes nitrogen is acting as a ligand or donor atom, and sometimes oxygen is acting as a donor atom. So these are called as ambidentate ligands. One more example of ambidentate ligand is thiocyanate, in which the ligand can attach through sulfur also and through nitrogen also. Okay, let's move forward to the next topic, that is the terms used in coordination chemistry. So terms used in coordination chemistry. The first term is coordination sphere. The first term is coordination sphere. Now let's understand what do you mean by coordination sphere. Now the central metal ion and the ligands are written in a square bracket, and this square bracket is nothing but your coordination sphere. The ionizable groups in the complex is written outside, and if the complex carries charge, then it is called as complex ion. Let us understand with the help of an example. Now we will see here K4FeCN6 complex. Okay, this will be written as this, and this will not ionize. This you can write it as this you can write it as like this. This is known as ionizable group. Okay, this is non-ionizable. So this is coordination sphere. This is your coordination sphere, and these are ionizable groups. So this is also known as your counter ion. Okay, this is also known as your counter ion. Now let's move to the next term used in charge number of the complex ion. Charge number of the complex ion and oxidation state of the metal. Oxidation state of the metal. So the next term used in coordination chemistry is the charge number of the complex ion and the oxidation state of the metal. The metal is nothing but the charge carried by the metal. Okay, nothing but the charge carried by the metal. And the charge number of the complex ion is nothing but the sum of the oxidation state of the metal and the charges of carried by the ligands. Let's see with the help of an example. I will take this example only. FeCN6 4 minus. This is your complex ion. Now what is the charge carried by the complex ion? Charge of the complex ion is, what it is? Minus 4. So charge, we have said that charge of the complex is nothing but your oxidation state of the metal, that is metal over here is Fe, plus the charges, that is charge of ligands, that is your cyanide. How many cyanide atoms are there? 6. So we can write, suppose we don't know the oxidation state of Fe. Okay, and we have to find the oxidation state of Fe using the charge of the complex and the charge of the cyanide. So how many cyanide atoms are there? 6. So each cyanide will donate, each cyanide is carrying one negative charge. So total 6 negative charges. So this we can write over here like this, that is oxidation state of Fe is equal to minus 6 plus 4, that is equal to 2. So in this way, using the charge of the complex ion, you can also find the oxidation state of the metal. This is important in solving problems also. Now the next term used is coordination number. Next term used in the coordination chemistry is the coordination number of the metal ion. Coordination number, that is, it is also represented as Cn of the metal ion. Let's see with the help of example. Cobalt. Now the cobalt complex over here, is having 4 atoms of ammonia and 2 of chloride. So it is having total 6 ligands, and 6 ligands, each of them is a monodentate ligand. So each of them, so how many total ligands are there? 6. So 6 pair of electrons are being donated to the cobalt, and so 6 coordinate bonds are formed with this by these 6 ligands with the cobalt. So coordination number of cobalt over here, cobalt is in +3 state. So here it is 6. Okay, but this is not the case with the bidentate ligand. Here remember that the ligands are monodentate. We have seen what do you mean by monodentate and bidentate as well as polydentate. The ligand attached to cobalt over here are monodentate. So let's see the example where the ligands are not monodentate. So for example, the next example of the complex will be cobalt attached to ethylene diamine. Okay. Now ethylene diamine, we have seen that it is a bidentate ligand. Now this complex, En is a abbreviation written for ethylene diamine. So 3 atoms of ethylene diamine are attached to cobalt. So we will find how many electron pairs are donated by the ligand to this cobalt. Again, each ethylene diamine donate 2 pair of electrons. So total 6 pair of electrons are donated to the cobalt, hence 6 coordinate bond are formed. So again we can see that coordination number of cobalt in this complex is also 6. So we have to remember, we can write it as coordination number of the metal ion is the number of ligands attached directly to it means to the metal ion, or number of electron pairs donated by the ligand in the coordinate in the complex formation. So coordination number of metal ion is the number of ligands attached directly to it. When we can say the number of ligands is equal to the coordination number only when the ligands are monodentate. But if the ligands are not monodentate, then we can say that the number of electron pairs donated by the ligands is equal to the coordination number of the central metal ion. Thank you.